Have you ever noticed how a swimming pool looks shallower than it really is, or how your legs seem shorter when you stand in water? These are not tricks of the eye, they're beautiful examples of the physics of refraction. Refraction is simply the bending of light when it moves from one medium to another, like from air into water or from water back into air. This bending changes the apparent position of objects, creating fascinating effects in our daily life. Remember the relation, refractive index, mu, equals real depth divided by apparent depth. This simple formula explains why things often appear raised or shifted. In this lesson, let's explore some real-world consequences of refraction that you've probably seen but never thought about deeply. Let's begin with something you see almost every night, the twinkling of stars. A star does not actually change its brightness constantly. The twinkling effect is caused by the Earth's atmosphere. As starlight enters, it passes through multiple layers of air at different temperatures. Since temperature changes the refractive index, the path of light keeps bending randomly. This makes the apparent position of the star shift continuously. Our eyes receive this changing light and the star seems to flicker. As you can see in the diagram, the starlight is bent differently by each layer of air, and this variation causes the twinkling we admire in the night sky. Here's another fascinating phenomenon. We actually see the sun before it has risen and even after it has set. How is that possible? The answer again lies in atmospheric refraction. When sunlight enters the Earth's atmosphere at a slant near the horizon, the rays bend downwards towards us. So, even when the sun is still below the horizon, the refracted rays reach our eyes, and we see the sun as if it were already above the horizon. Similarly, after the sun has dipped below, refraction allows us to see it for a few extra minutes. On average, this gives us about 2 minutes of early sunrise and 2 minutes of delayed sunset. As shown in the diagram, the apparent position of the sun is slightly above the real position due to bending of rays. Now let's move from the skies to something you can try at home, the coin in a vessel experiment. Place a coin at the bottom of a vessel and step back until it disappears from view. Now, ask someone to pour water into the vessel without changing your position. Suddenly, the coin becomes visible again. Why? Because the rays of light from the coin bend away from the normal as they travel from water to air. Your eye traces these rays backward in a straight line and perceives the coin at a higher position than it really is. This is a simple but powerful demonstration of apparent depth due to refraction, the same effect that makes a swimming pool floor appear raised. Let's extend this idea to solids. Imagine a printed page beneath a thick glass slab. When you look at it from above, the print seems raised. This happens because glass has a higher refractive index than air. Light rays from the print bend as they leave the glass, and your eyes trace them back to a virtual image that is nearer to you. The same applies to a piece of paper stuck to the bottom of a glass slab. It too appears closer than it really is. As shown in the ray diagram for a parallel-sided glass slab, the incident and emergent rays are parallel, but the image is shifted upward, creating the illusion of raised text or objects. Next, let's talk about why tanks and pools appear shallower than they actually are. Suppose a tank is 3 meters deep. To an observer outside, the bottom will appear at only 2.25 meters depth. Why? Because apparent depth equals real depth divided by refractive index. For water, mu is approximately 4 by 3. So, 3 divided by 4 by 3 equals 2.25 meters. The same happens when you stand in a tank. Your legs, being submerged, appear shorter than their real length. This is a classic example of how refraction affects our perception of depth and size. Let's quickly recap everything we've learned today. We saw how atmospheric refraction makes stars twinkle and allows us to witness early sunrise and delayed sunset. We also explored laboratory-style experiments, a coin reappearing in water, raised images through a glass slab, and tanks appearing shallower than they are. The common principle is that refraction changes the apparent position of objects. The Gunning relation is refractive index equals real depth divided by apparent depth. These consequences are not just curiosities, they are applied in telescope design, underwater optics, and even in correcting illusions for safe construction of swimming pools and aquariums. So the next time you see your legs look short in water or watch the first rays of the sun, you'll know it's not an illusion, it's physics.